Yeah, good evening. Welcome to the live session of problem solving session, fourth problem solving session on manufacturing process casting and joining. My name is Rakesh. I'm TA for this course. I will be covering this fourth week session of this course. So, I'll start with the recap that what are the different topics that was discussed during this week. So these are the various uh, topics. So we started with the solidification of weld. Then there was discussion on different types of welding process. There was introduction on solid state welding, such as ultrasonic, and then there was this liquid state welding, such as electron beam, laser beam, plasma arc welding. Then there is this arc welding. A good discussion is on arc welding. Then followed by the other types of welding process. This was the last topic, heat affected zone. We also discussed that which is the weakest area of the weld. So this size of heat affected zone increases with lowering input rate process such as uh, laser beam welding, submerged arc welding, or gas metal arc welding, and gas welding, and then also with the decreasing welding speed, and then increase thermal conductivity of the base metal and decrease in the base metal thickness. Okay, and the heat effect can be minimized after this was the post processing treatment such as heat treatment. Okay, so these were the different parameters that we need to keep in mind before selecting this any process. So we should take care of this metal thickness, and we should take care of thermal conductivity, and then welding speed, and then heat input. According to these things, we have to select the process. So this comes under the different welding process. Okay. So let us start with this solid state or phase welding. So basically, in this, liquid is not present. So whatever the bonding that is going to happen, it is completely due to the plastic deformation, and such as high strain rate deformation. So here the high temperature promotes bonding, such as along with the pressure also promotes this bonding, and it does not require any kind of electrodes or shielding gases or fluxes where it was required in arc welding. Okay, arc or gas welding. So let us discuss one by one. So first one is the forge welding. So this was a very bold technique in which we just heat the metal, and then we use the open hammer to get that shape, required shape. Okay. Then we have also this butt welding, in which surfaces are brought into contact, heated by the electric current, and axially compressed. So there was no rotation involved. So whereas in friction welding, we have one piece rotating and other piece is stationary. So that is discussed. This, such as this, the third process, that is friction welding. Okay. So in this, one workpiece is rotated, and the other one means there are two workpieces. If you want to join both, one is held stationary and one is rotated. And then at the end, the pressure is applied to establish the twist. the bond between these two. Okay, that is friction welding. And then we have explosive welding. These are the different types of solid state welding. We have explosive welding as well. So this mainly used for joining dissimilar metals. So you see, we have a detonator here, and then we detonate from here. So the shock wave will travel so that the bonding happens in sequence. That's why we provide some offset angle, some 15 to 25 degrees angle. Okay, there were so the bond actually depends on different parameters such as angle and the flare plate and then spacing, all these things. Okay. Then Then we have resistance welding. I think, okay, let me switch back to normal. So then we have resistance welding, in which we take the advantage of this resistance of a material, like electrical resistance. The process uses electrical resistance uh, between the two members that are going to jab it. And the heat generated is equal to I square R T, whereas I is the current, R is the resistance, and T is the time. Okay. For high heat generation at the junction, workpiece contact resistance should be kept high and the rest should be kept low. Okay. Then we have we'll discuss in detail. This is just an introduction. So then we have so these are the different types of resistance welding. One is the spot welding. So very common to join two metals. So these are the water cooled copper electrodes, and these are very thin sheets. When you apply some pressure, so at the interface we are going to get this weld joint. Then we have projection welding, in which similar to the spot welding, except we have projections here instead of the plain flat plane. We have a projections, and at which this welding is going to happen. Similarly, we have resistance seam welding, which is very popular to join big barrels, big sheets. Okay, some of the examples is given here. So these are the wheel electrodes that are going to join these two sheets. Then we have overlapping spot welds. Then we have spot welds with nuggets. So we see nuggets here. Okay, it's not continuous. Then we have a resistance welded gasoline tank. So this edge is welded by this seam welding. Okay, resistance seam welding. Okay, then let us move on. So then we have this ultrasonic welding. So here we take the advantage of this very high frequency oscillations. So here we will take this oscillatory shear stress of the ultrasonic frequency, which is going to be applied between two parallel sheets. One is kept stationary and one is vibrating at very ultrasonic frequency. It will be around 20,000 hertz to say 30,000 hertz frequency. Okay. So this oscillatory motion break down any surface films to allow intimate contact and strong metallurgical bond. Okay, this we have to keep in mind. If you this also can be used for joining dissimilar metals as well. Okay. But the temperatures that are going to develop is well below the melting point of the parent material. Okay, no fillers are used, no fluxes are used, no shielding gases are used. So no heat affected zone is going to happen in this ultrasonic welding. But generally limited to lab joints and soft materials such as aluminum and copper. And and also there is a geometric constraint. We cannot use this method in everywhere. So we have only for lab joints we can use this. So this is the typical setup of ultrasonic welding. So basically we will have some vibrating mass, then we have a transducer, then we have a tip, sonotube tip, and then we have a plates. One is connected to this sonotube tip and one is held stationary in the anvil. Okay, in the second side you can see how the vibratory motion is being transferred to the workpiece, and then from that from there, so at the here at the interface the bond is going to happen. Okay, this is how it was. So I think you already know about this transducer. So when you apply this electrical energy, it is going to convert into mechanical energy. Okay, in this alternating transducer. So we can use magnetostrictive materials or piezoelectric materials to get this very high frequency. Okay. Then these are some of the applications of this ultrasonic welding. So wire terminators and splicing in electrical and electronic industries, uh, which eliminate this soldering purpose. Then we have also used for assembly of aluminum sheet metal panels, welding of tubes to sheet in solar panels. So this is very highly used application for solar panels. Small parts assembly task in automotive industries. Okay, but these applications are limited to small parts, unlike the other process that we are going to discuss. So let us start with some of this welding process in which we are going to have very high heat input rate. Here we are the previous solid state welding. We are not melting the parent material, but we are deforming plastically, and we are applying with or without pressure. The bond is going to be established. But in this liquid state process, the parent material is going to be melted with some heat energy. So here, so this is a typical electron beam welding setup. So we have a cathode which and we have an anode. So this one. So when you apply some potential difference between two, so this we are going to get some electrons cloud from this cathode, and we are going to be focused, and we going to deflection, so that we can move the electron beam, and then we are going to establish this welding. So these focusing and deflection coils are made of electromagnetic coils, and everything is maintained in the vacuum to avoid this collision with the air particles. Okay, this is very high intensity beam. So we are going to get very so if you actually see that weld joint which is made by electron beam, you can appreciate this welding technique. So we'll have a very so if this is the one, we will have a very high penetration but with very less deviance. Okay, and very nicely established joint. See, so we are having typically this is the heat input rate when compared with other. It was approximately twice the other welding process. So here we are going to convert this kinetic energy of the electrons into the heat, which are going to strike the parent material, and then which is going to be melted as well as vaporize the material. So we are going to get very high temperature of this at the welding zone as well. Since it is very high heat inputted, we are going to get very less heat effector zone as well. So as I discussed, the penetration will be very high, producing deep, narrow, parallel-sided fusion zones with narrow heat affected zones. Since your heat input rate or heat density is very high, so this energy density. Okay. So this is the working principle. So electron beams are produced in what called gun thermomechanically, extracting them from a heated element or cathode and accelerating them across the high potential HUD using one or more annular anodes along a vacuum column. The stream of the accelerated electrons is focused into the beam of very high energy density using a series of electromagnetic coils. These electromagnetic coils are these focusing and deflection coils. The electrons then pass from the column to the work chamber to the workpiece to produce the weld. So this is the typical working principle that I have already explained. Then we are going to discuss about the second type, that is the laser beam welding. So similar concept, but here we are going to use this laser energy. So this, I think you might well aware of this working principle of laser. Uh, So basically, we will have a, so for example, this is Ruby or some source material in which can generate this laser from it. So basically, we'll have a 100% reflecting mirror and partially reflecting mirror. So so we'll have this population inversion when it so happens. So we'll have very high intensity of this beam, which are going to be concentrated from a central source. Okay, which are directional, and then they are converged into the very small area. Okay. Hence, we are going to establish this build. So let us see different aspects of this laser beam welding. So here we are going to use very high intensity beam of electromagnetic energy as the heating source for welding the form of photons. So here also the heat energy density is very high, similar to the electrobeam welding. So here the conversion of kinetic energy of the photons into heat occurs as these particles strike the workpiece, leading to melting and vaporization. Similar, it was very similar to this electron beam welding. Okay. So shielding for laser beam welding process action accomplished with kinetic gases either in dry boxes or from a special shroud over the vicinity of the weld puddle, although the process could also be performed in vacuum. Okay. So this has to be performed in vacuum, this electron beam welding. Similarly, laser beam can be performed in vacuum as well as in air atmosphere. Okay, then let us discuss this plasma arc. So here we are going to establish this very high temperature plasma arc. Generally, this temperature is too high. Generally, we use this plasma arc only for the cutting. Okay, this is similar, except we are going to get plasma due to the ionization of this the air that is going to happen. We are having plasma gas as well as shielding gas to protect the weld zone. Then we are having non-consumable electrode and then shielding gas nozzle as well as constricting water cooled nozzle as well. Okay, let us discuss about plasma quelling. So this plasma is a gaseous mixture of positive ions, electrons, and neutral gas molecules, which are in for which we are going to apply very high potential. So plasma welding is the welding process utilizing heat generated by the constricted arc stuck between a tungsten and non-consumable electrode and the workpiece. Okay. Then the transfer arc process produce plasma jet of high energy density and may be used for high speed welding and cutting of ceramic, steels, aluminum alloys, copper alloys, titanium alloys, and nickel alloys. So generally, basically, we mostly use this arc welding for cutting, also for welding as well. So these are the advantages. Require very less operator skills since we are having very less deviations or no misalignments for the beam, and we have very high welding rates, very high penetrating capability such as keyhole effect. Disadvantage of plasma arc is very expensive and high distortion wire wells as a result of high heat input rate. It transferred in high arc process. So this keyhole is nothing but suppose if you are welding this two joints, okay. So when you meld this thing, so this is the keyhole that is going to be formed. So this is the plasma arc, you can say, or laser beam or electron beam. So this is the keyhole that is going to travel further, okay, and this is going to decide the welding characteristics of this formation. This is the keyhole that is going to be established. Then let us move on. So we have let us start with arc welding. So we discussed solid state welding, then we came to different types of this high energy density welding process such as laser beam welding, electron beam welding, plasma arc welding. Then we going to discuss this arc welding, which is popularly used everywhere. So this is a typical arc welding process. So these are the different terminology that we are going to use. That is, one is the core wire, which will be coated with the flux materials. Then we have a weld pool, which is near just below this electrode. Then we have a deposited welded, and we are going to have slag, which has to be removed after the job. So this is a cross section of welding. So this was developed very early 1800s. Uses a consumable or non-consumable electrode. Arc is positioned between the tips of the electrode and the workpiece to be welded. Arc is started by momentarily touching the electrode. So we'll discuss all these concepts. So this is the typical basic principle of arc welding. So initially we have two parts that are going to be joined, and this is the cross-sectional view. So here we are seeing from this direction. Okay, so here I have explained everything. So here we have an electrode, and we are using filler from the external source. Then we have a shielding gas to protect the weld fluid from the atmosphere. Okay. And finally, we are going to get this weld. weld between the two pellets, and this is called the penetration, and this is called the rain. This top portion is called reinforcement. So let us see this arc schematic diagram. So basically, I think I have already explained these things to you. So electrode we can use consumable as well as non-consumable. But if you are using consumable electrode, provide the source of the filler metal in the arc welding, available in two principal forms: rods and wires. Arc shielding. So we can shield the weld pool using argon, helium, or both, which are inert, which are not going to react with the weld pool. A flux also can be used. So if you are not using this shielding gases, you can use flux, which are going to absorb the dissolved gases and keep the and form a layer and protect the weld pool. Arc welding with coated electrodes, the coating serves following purpose: shields the metal pool from the atmosphere contamination. It acts as a carrier for alloying elements or deoxidants electron. This flux, the main aspects of flux is to protect the weld zone from the atmosphere, stabilize the arc, and reduce spattering. So this is the temperature that is going to be generated in arc welding. So now let us. So I think you are all familiar with how to start an electric arc. So there are two methods. One is touch start method. So in touch start method, you are going to touch the base metal with the electric arc. Then you are going to keep the electrode at a distance so that the arc is established and we proceed with it. So this is called a touch start method. The electrode is brought in contact with the workpiece and then pulled apart to create very small gap. Due to direct contact, short circuiting happens, resulting large current flow leading to heating, partially melting and slight evaporation of the workpiece metal at electrode tip. Heating of the electrode releases electrons due to the thermal ionization. Vaporization of metal also produces ions and electrons. Upon withdrawal of the electrode, flow of current starts to these charged particles and arc is initiated. This is what happens behind this process of touch start method. So similarly, we have other method, that is field start method. Better we see this schematic. So initially we are going to short circuit it, then we are going to move a bit so that the arc is established, and we continue the process. In other process, we are not going to touch the which is field start method. We are not going to touch the surface, but initial we'll keep it at a distance, and we are going to apply very high potential difference so that the arc is established. So which it can be around 10 volts. Basically, we use this for automated process. So these are the arc welding characteristics. So the process is applicable to all metals, all alloys except pure copper, aluminum, and slow metal points. Since basically what happens is, so on the surface of this copper and pure aluminum, this oxide layer is going to form, which is going to hinder this formation of arc. So that's why we are not will not encourage using this for this copper and aluminum. And use of electrode coatings shields a weld pool from the atmosphere contamination by creating suitable gaseous atmosphere and slag. Slag also refines the molten metal. Okay, so this is the basic use of this slag. Acts as a carrier of alloying elements or deoxidates and other elements necessary to produce desired arc. Okay, so this is the temperature and this is the powers and this is the thickness of the weld pool. So we have basically two types of arc welding. One is with use of consumable and non-consumable electrode. So we'll see different types. First, let us discuss about consumable electrodes. So these forms of consumable electrodes, weld rods, also called sticks, are 9 to 18 inches and 3 inches are less in diameter and must be changed periodically. So that is the main disadvantages using these consumable electrodes. We have to continuously change if you are going to use these sticks. Weld wire can be continuously fed from glue with long length of wires and avoiding frequent interruptions. So this, but it is going to be expensive. In both rods and wire forms, electrode is consumed by arc and added to the weld joint as a filler material. Okay. But in case of non-consumable electrode, the electrode is made of tungsten, which resists melting. gradually depleted during welding. So we can use either filler material. We cannot. There is no need to use filler material as well. So we have different types of power source. AC is the economical power source that can be used. DC, but less expensive, but generally restricted to ferrous metals. But DC is more stable. It will better for the stable arc, but is going to be not economically viable. So we have, let us discuss about this. These are the different types of arc welding process. We have shielded metal arc welding, gas metal arc welding, flux core arc welding, electrogas welding, and submerged arc welding. We will discuss each thing. Before that, let us discuss about this current voltage characteristics of an arc. So we are actually we what we are going to see is, so we have a parent material and we are going to get an arc. So let us say this is arc. So we have electrode. So now let us understand what this arc made of. So basically, with increase in current, we see that voltage is decreasing at an instant, and then it is going to be constant. For a given electrode material, voltage reduces with increasing current up to 50 amps, and then increases thereafter, slow. But the slope of increase is very less. Until 50 amps, basically the shape of arc is almost cylindrical. Okay, this is this arc shape. So then surface to volume ratio decreases with increase in radius. So if you see surface to volume ratio, surface is 2 times pi over d square plus pi d into h. Okay, divided by the volume. So top surface area and then later surface area divided by it. So then if you see the surface volume ratio decreases with increase in ratio. So with increase in radius or increase in diameter, this surface to volume ratio is going to increase. Sorry, decrease. So this A by V is going to decrease with respect to increase in ratio, because this is r square and this is r cube. So this increase in radius will decrease this surface to volume ratio. Surface to volume ratio will decrease as radius increases, since the R is in the denominator. So until 50 amps, the arc radius increases. So the arc radius is increasing. If the arc radius is increasing, the surface to volume ratio dissipates less heat, connectivity increases, resistance R decreases, voltage R decreases. Okay. So if R is decreasing, so that results in dissipates less heat, heat is less, conductivity is less, but R is also less, but voltage is also less. This is what happens below 50 amps. But above 50 amps, we are going to get this bulge in arc bulge. Say this. So before it was like this, then we are going to get this bulge. Because the arc bulges out, the current path becomes more than arc gap. Resistance to current flow increase and the voltage increases. Okay, so that is the reason. Since that is the reason why this bulge is going to happen. Okay, that is the current characteristics. You can say current voltage characteristics of an arc. So let us now see different types of polarities. So basically, we have two types of polarities. That is the straight polarity and then reverse polarity. So generally, the workpiece is positive. Okay, that is this the weld that is going to we are going to make the weld is going to be positive, and then the weld will be negative. Okay, that is the circuit, how the circuit closes. That is the straight polarity. So then direct current extracts electrode is negative and workpiece is positive. This metal produce deep narrow weld joints. Okay, that is called direct current electron negative. Similarly, if you reverse the polarity, that is reverse polarity, that is direct current electrode positive, so we are going to get shallow weld. So this can be used for sheets of thickness. Then we have alternating current in which we are going to get in between this straight and reverse polarity. We'll see where we are going to use this AC current as well. So let us discuss the second first one, that is shielded metal arc welding. So the famously typically used everywhere. So in this we are going to the shielded is the shielding of this weld pool is going to happen using the flux that you are going to use. So the electrodes that are made with the coating on the surface. So wherever the building that we are going to see in nearby places are practically this is submerged arc welding. So in which you see that they are having some holder to hold the weld and then they're going to do the welding. Okay, so these are called sticks or welding. So these are called, the electrodes are called sticks. So you can also call it as stick welding. So if you see, this is the terminology used. We have a consumable electrode and the electrode coating on the surface. Then we have a slag that we have to remove after the welding. Then we have a solidified weld metal and then mortal weld metal and the base metal. And we have protective gas from the electrode coating, and this is the direction of welding. So these are the different types of uh, like characteristics of this submerged arc welding. The composition of filler metal usually close to the base metal. The- So this is so basically this is need when the welding gap is too high. We need so the parent material, even the parent material melt. So we need a filler material to fill the gap. It also coating consists of powdered. So this flux is made of this cellulose mixed with oxides, carbonates, and other ingredients held together by silicate binder. Okay, this is the flux material that is going to be used. Welding stick is clamped in electrode holder connected to power source. Okay, but the disadvantage is the sticks has to be changed periodically, so that going to reduce your performance. High current levels may melt coating prematurely as well. This is mainly used for steel, stainless steels, cast irons, and non-ferrous alloys, but non-used for aluminum and alloys and copper alloys and titanium, as I discussed about because of the formation of this oxide surface layer. So then let us see this gas metal arc welding. So shielded metal arc welding, we are not using any shielded gas. So the flux is melting and it is forming a shield. But in gas metal arc welding, so if you see this gas metal, so this metal represents we are going to use a consumable electrode, and then gas represents we are going to use a shielding gas. So uses a consumable bare metal wire as electrode and shielding accomplished by flooding arc with a gas. Flooding a arc with a gas. Wire is fed continuously and automatically from the spool through a welding gun. Shielding gases include inert gases such as argon, helium from aluminum welding, and active gas such as CO2 for steel welding. So bare electrodes wire uses shield gases, eliminates slag covering on the weld bit. No need for manual grinding and cleaning of the slag. So there, since we are not using any flux, there is no you to clean the weld. So this is how it looks. So we have a wire coming from the spool. Then we have a slot for providing the shielding gas. So this is the shielding gas that is going to protect the weld zone. We have a nozzle, we have a shielding gun, shielding gas, and we have electrode wire, and we have direction of travel. So this is the molten metal, and this is the base metal. Okay, this is the gas metal welding. So this is how it looks. So this we also call this as MIG, or metal inert gas welding, or gas metal arc welding. Okay, so this is how it looks. In we discussed everything similar. So we use argon, helium, CO2 for shielding, used for welding a variety of ferrous and non-ferrous use. The coiled electrode wire is fed by drive rolls as it melts everything. Except for aluminium, a DC source is used with the consumable electrode as positive terminal. So for aluminium, so this oxide layer is going to form. So if you use AC, it is observed that this AC will improve the quality of weld. So our use of the weld. So we have a current density around 10,000 here, and welding currents we are going to use around 300 amps. So these are the advantages over the shielded metal arc welding for the MIG, that is metal inert gas welding. So better arc time because of the continuous wire electrode. But in case of submerged arc welding, we are going to use sticks, which has to be periodically changed. And then we have better use of electrode filler metal than submerged arc welding. We have very high deposition rates and eliminate problems drag removal, as uh, also the process can be automated. So these are the different types of advantages of this MIG welding over this shielded metal arc welding. So now let us see different types of arc welding process which does not use consumable electrodes, such as gas tungsten arc welding. So this gas represents there is a shielding gas, and this tungsten represents we are using non-consumable electrode. So these are the key terms that tells about this process. Then we have plasma arc welding. When we have carbon arc welding, we have stud welding. Okay. So let us discuss about this gas tungsten arc welding. So as I said, we are using a non-consumable tungsten electrode and an inert gas for arc shielding. So the amount of melting point of tungsten is very high. So it is not going to melt it that easily. Also, this is also called TIG welding. As we called metal inert gas as MIG welding, we can also call this TIG as well as WIG welding. Used with or without filler metal. When used, filler metal is added to weld put from separate rod or wire. Applications: aluminum, stainless steel, and most common. Okay, this is how the stick welding going to look. So we are not having any external filler, internal filler. So if you want, you can add this filler metal from the from external source. So we generally use all the parameters is same as MIG welding except this use of non-consumable electrode. We use argon, helium are combined for this shielding. We can use AC DC mode operation. We can AC is prefer aluminum ignition because of the cleaning action of AC removes oxide and improves weld quality. And GTAW provides very clean welds since no flux is employed. Particularly attractive for reactive material and high temperature refractory metals. Okay, this is typical. This provides very nice and seamless welding. It's seam welding, but very clear welding surface as well. So these are the advantages and disadvantages of TIG welding. Very high quality weld for suitable applications. No spatter because of no filler metal that we are going to use. Little or no post welding cleaning because of no flux that we are going to use. But the only disadvantage is generally slower and more costlier than consumable electrode. Okay, in arc welding process, in all the arc welding process. Then let us see this very popular welding process, that is submerged arc welding. So only in submerged arc welding we are going to use this flux hopper, which is granular flux that we are going to see. So you see this black portion, that is the flux. Okay, granular flux. So the flux is completely covered. The weld pool is completely covered with flux, under which this arc welding is going to happen. That's why this is called submerged arc welding. Okay, so, and we have a flux hopper which provides the flux, and we have a other tube which is going to recover this flux, and the process repeats itself. So the flux is basically lime, SiO2, magnesium oxide, and CF2. Flux is fed into weld zone by gravity. So this is also a disadvantages. So we cannot use this process inverted. So thick layer of flux covers the molten metal, prevents oxidation, sparks, reduce weld spatter, increase deposition efficiency, acts as thermal insulator, promotes deep penetration. Okay, limited welds in flat because this flux is assisted only by gravity. Can weld a variety of carbon alloy and stainless steel sheets on plate, often at speed as high as 5 meter per minute is very impressive in welding. Uh, that only possible with this type of welding. Quality of weld is very high with good toughness, ductility, and uniform properties. Thick plate welding for ship building. So mostly these are used in thick welding for ship building and pressure vessels. So now let us see this gas welding. So in gas welding, so I think we have physically seen this gas welding in many cases as well. So generally we use this acetylene common fuel, which is very impressive. So we put this C2H2 acetylene when combined with oxygen, it releases 33% of heat, and then the produced CO when reacts with hydrogen, it produces 67% of heat, which is secondary one. Okay. And temperatures can be achieved at 3000 degrees Celsius. So this is a typical torch, how the torch looks. So we have two valves to control this oxygen and hydrogen that is going to be released. Okay, sorry, acetylene, and then oxygen gas. Okay, then we have a mixer in which the both are going to be mixed, and then it, we are going to weld. So this also used for cutting as well. So if you increase this oxygen level, so the full force which is going to burn away the metal, so this can be used as cutting. This can be used in cutting as well. So currently I don't have any parts to show, but that is how it happens. So we have different types of flames. One is neutral, oxidizing, reducing flames. So only in neutral flame we are going to use the same ratio of oxygen to acetylene gas. In oxidizing flame we are giving excessive oxygen, so used for copper coverage less because it forms protective oxide film. For reducing flame we are using less oxygen than required. It also called carburizing flame, used for soldering, brazing, and flame hardening. I think you might have heard about flame hardening as well. So this is used for low carbon steels. So in which the surface, if you heat with this carburizing flame, the surface is going to the carbon is going to diffuse into the surface, and it is going to harden the surface. So we have types of flames as I discussed. One is the neutral flame, an oxidizing flame, and a carburizing flame. So only in neutral flame we are going to use this 1:1 ratio of oxygen to acetylene ratio. And then greater oxygen supplies, the flame is known oxidizing flame. It can be harmful, especially for steel, because it oxidizes the metal. If the oxygen is insufficient for combustion, the flame is known as carburizing flame. So by color also you can identify. So bright luminous inner core are blue envelope, it is carburizing. Inner core pointed, outer and core small and narrow, oxidizing, and is very large flame. You can say as neutral flame. So in the same scenario as arc welding, in gas welding also we can use bare or flux coated. Metal at high temperature tend to react with chemically with elements in air and oxygen and nitrogen. So that you have to provide some shielding here because there is no shielding in this gas metal arc welding. Oxygen and nitrogen destroy the strength and toughness of the weld joint. So these are the, like kind of disadvantages I could say. So flux treated oxidation by generating gaseous shield around the weld. So that's why we have to use this flux. Dissolves and removes oxide in the form of slag. Slag protects the metal against the oxidation acids. But again, with the use of slag, we are going to have different problems as well. But advantage is very economical, portable, and versatile, and economical for low quantities. So producing this acetylene gas is very simple. Means we just need a big chamber in which we have to sprinkle water in the chemical, and then it's going to release this acetylene gas. An arc is in the characteristic and flowing between two electrodes through an hydrogen column. Arc is generated by electron liberation. So we'll see. So next one is the thermite welding. So this is very popular for joining this railway railroads. Basically, we have a thermite mixture, which is 1:3 ratio of aluminum to iron oxide. So when you combine these two and when you start the reaction, so we are going to get heat which is going to enough to get completely melt the this iron oxide, and then it is going to form Al2O3 aluminum oxide, which is going to be floated on the surface and which can be easily removed. Then we have different types of solids and liquid state welding process, such as brazing and soldering. So that only difference between brazing and soldering is the temperature that we are going to operate. So both are used for joining materials that cannot withstand high temperatures, such as electronic components. Join parts that are delicate and intricate. Join two or more metals with very different characteristics, such as thickness or cross section. Filler metal is placed at or between the surfaces to be joined. Temperature is raised to melt the filler metal, but not the workpiece. Molten metal fills the closely filled space by capillary reactions. Upon cooling and solidification of metal, the strong joint is established. Temperature of operation differential brazing from the shouldering. Okay, that is what I discussed initially. Let us see with the brazing. So joining process in which the filler metal is melted and distributed with capillary action between the paying surfaces of the metal being joined. So this has to be kept in mind. The temperature that we work is above 450 degrees Celsius, but less than the melting point of the parent material. Okay, 450 degrees Celsius is the brazing temperature. Dissimilar metals can be assembled with good joint strength. So typical products are carbide drills that are going to be attached with a steel shaft. Intricate light shape can be joined with a little distortion. So this is mostly about this brazing technique. So let us see about the soldering as well, which is I think very well known. But the temperature that we are going to operate is less than 450 degrees Celsius, and then the rest of the characteristics are being the same. So no melting of base metals, but filler metals weights the combines with the base metal to form metallurgical bond. And so the base metal is not practically melting. Used extensively in the electronic industries because shoulders do not generally have enough strength. They are not used for load bearing applications. Can join various metal thickness, copper, AG, AU are easy to shoulder. Aluminium SS are difficult to shoulder because of their strong thin oxide film. Okay. So these are the advantages of brazing compared to welding. Uh, so any metals can be joined, including dissimilar metals. In this process, can be performed quickly and constantly, permitting high production rates. Multiple joints can be brazed simultaneously. In general, less heat power required for the this process. So there is no problem with this heat effect zone since the heat density is very less. Joint areas that are inaccessible and the temperature generated is very less to cause this deform recrystallization in the parent material. Joints areas that are inaccessible with the other process can be possible with this process because of the capillary reaction. So that is the advantage of it. So let us see the last topic in this series. That is the welding defects. So the first defect is the cracking defect. So this is a welding crack that is occurred. So basically, due to this mismatch in the other residual stresses that are going to be generated in the crack. Okay. So the prevention is change the weld design to minimize the stresses from shrinkage, or preheat the weld joints before performing this joining process, and avoid rapid cooling of the components after welding. Okay. Cracking. Then we have incomplete fusion or penetration. Okay. So produce poor weld beats due to insufficient heat input. So we have to raise the temperature to avoid this. We have to clean the weld before welding, and we have to use adequate shielding gases and change the design of joints and types of electrodes. So you see, this is going to be the common error in every region. That is design of joints, and the selector of electrode should be very careful to avoid these type of defects. Then we have porosity defect. This is very similar to the casting products as well, which is caused to the entrapped gases during solidification of the weld area, chemical reactions during welding or contaminations. So we can eliminate by using this electrodes and filler material or preheating the weld area. Also, we can use flux or degassing agents, proper cleaning and preventing contamination from the entering the weld zone. That is how we eradicate this porosity. Then we have slag inclusion. If suppose you are using any slags, these inclusions are compounds such as oxides of fluxes and electrode coating metals that are entrapped, that are trapped into the weld zones. How to avoid this? Clean the weld bead surface before the next layer is deposited. Provide adequate shielding gas. Change the type of electrode. Then we have this bad profile. So it will not be even. There will be undercut or over excessive reinforcement. And the other side we will have this oxide inclusions as similar to the slag inclusions. So this occurs due to underfilling or overfilling and melting away the base metal. Okay, then how to prevent this is to improve the welding technique. So this is the basic error that causes these defects. Then select proper selection of the electrode and filler metal should be appropriate to avoid these tips or defects. So I let us take some 5-10 minutes break. So let 5 minutes break. Let us meet around 7 or 5. Okay, then we'll discuss some of the numericals and some of the problems. So that gives an idea on these sessions. Okay. Okay, so let us discuss some of the problems on this topic one by one. So I will give some 2 3 minutes time to read the question, so you can answer, and then I will discuss later. Okay, let me discuss. So the question is about heat affected zone. The size of heat affected zone in welding increases with. So I think this is the first slide that I have decreased. The first one is with decrease in welding speed. Yeah, this is true. Increase in base metal thickness. This is wrong because with decrease in base metal thickness, the heat affected zone will increase. So higher input rate process. No. Increase thermal conductivity of the base metal. This is true. Increase hardness of the metal to weld. This is wrong. So only one and four are the correct option. So option B will be the appropriate for this question. Just refer to the first, I think, first 2 3 slides on which we just started discussing on this heat affected zone. Okay, let us move to the next question. Okay. We'll see. So this is the correct statement we need to figure out. The first option is resistance welding process make use of heat generated by electrical resistance to achieve fusion of two parts to be joined. No pressure is used in this process and no filler material is used. In some resistance welding process, we use this pressure as well. So we'll move to the next. Copper is relatively easy to weld because its thermal conductivity is high. Uh, no, it does not depend on this thermal conductivity. Okay. So the second option is also wrong. Then third option. So if you see first option is wrong and second option is wrong, so that avoids leaves me the only one option D, which is correct. Okay. If so, for example, in second option, if the thermal conductivity is very high, so as you welding that his heat is getting dissipated, so there is no welding happening. So we need very high heat input rate, which is going to be complex welding. So that's why second option is wrong. So let us. So we know the answer, but just we'll read. Oxy-acetylene welding is the most widely used oxy-fuel welding process because acetylene mixed with an equal volume of air burns hotter than any other commercial element, which is true. An electric arc is a discharge of current across the gap in the electrical circuit, which is correct. The arc is sustained in arc welding process by transfer of molten metal across the gap. So this is wrong between the electrodes. It is sustained because of this establishment of the electrons that is being exchanged from the uh, positive to negative to positive. In that process, the heat is melting the electrode more, and then it is getting deposited on the weld. Then we have fifth option: metal with high resistivity are generally is tube. This is correct. So, will the heat input rate is easily established, so you can easily weld the metal. So, option D will be the appropriate for this question. Let us move to the next question. Answer the question number 3 and 4. I will discuss it around 7:20. Okay. Yeah, let us discuss. So the first question is about ultrasonic welding process. So to remove surface films to allow intimate contact and strong metallurgical bonding with the surface in the ultrasonic process. Interface surfaces are chemical. So the first option is interface surfaces are chemically cleaned before welding. Interface surfaces are heated up above the melting temperature of the parts. This is completely wrong. Oscillatory shear force of ultrasonic frequencies are applied to the interface, which is the correct option. Yeah. So the next one is electron beam welding process is performed in vacuum. So the because otherwise the electrons are lose their energy by colliding with air, which is correct. To increase the productivity round, to make the process economical round, to weld, basically it is going to increase the cost. To weld intricate shapes more accurately and at first, which is wrong. So first option is C, and the second option will be A. Okay. Okay, then let us move to the next question. Okay, let me solve slowly. So the fifth question is about electrical resistance between the two members to be joined is used as the heat source in the following process. So the electrical resistance is used for joining this tool. So first one is electric arc, projection welding, friction welding, and ultrasonic welding. So which will be the suitable answer? It's a resistance welding, right? And then projection welding is one of its type. So option B will be the correct one. If you remember the projection welding, so it has this spikes on which, so this is connected to an electrode and this is connected to an electrode. And then at this uh, spots, the welding is going to happen because of the electrical resistance. So this is called projection welding, and so option B will be the correct one. Then next one is welding of tubes to sheets in solar panel is commonly performed using the following process. So I have mentioned while explaining the specific. So we've only here this solar panels in only one welding process. So let me go back once. Okay. So in ultrasonic welding only, welding of tubes to sheets in solar panels. So this is the only application, main application in ultrasonic welding I have mentioned. So the correct option will be this solar panels, ultrasonic welding. Okay, so some of the applications are very specific to the welding process, so that we need to remember. For example, is in this case, joining of the tubes to the solar panels is only through ultrasonic, and also the battery plates are also welded using this ultrasonic, and then electronic are thin, delicate are welded using brazing or soldering. Mostly in electronic, we are going to use this soldering technique. So let us move to the next question. Okay. Yeah, good. So electrode coating in electric arc welding is used for shielding will pull from the atmospheric contamination. This is correct, and creating a suitable gaseous atmosphere and slag. That is also correct. Acting as a carrier for alloying elements. That is also correct. And then refining the molten metal. Yeah, that is also correct. So option E will be the correct option. Okay, this is also coating material. In some cases, we can also call as a flux material, along with some other alloying elements, which is mainly made of the similar to the base material. Okay, let us move to the next question. Yes. So in arc welding, the voltage increases sharply as current increases till 50 amps because until 50 amps current. So this I have discussed. If you see that graph, voltage versus current. So you'll see this kind of. So current is an x-axis and voltage in y-axis. So till 50 amps, you'll see decreasing, and then after it will be increasing. The reason, what is the reason? The arc dissipates more heat since its radius increases and sharp shape remains cylindrical. The so basically below 50 amps, so we are going to get a cylindrical arc typically. So the surface to volume ratio increases as surface to volume ratio decreases as R increases. Okay, if R increases, R the resistance decreases and the voltage decreases. Okay, that is the reason behind this, you know, strategy. So this is radius and this is resistance and voltage. And since surface to volume ratio is less, so the heat dissipation is also less. So the arc dissipates more heat. No, this is wrong. The heat dissipation is less if below 50 amps. Because of the increase in radius, the S by value is less. So the heat dissipation is more. But heat dissipation is more, but radius is decreasing and the shape remains cylindrical. Actually, it dissipates less heat. This is wrong. With increase in radius because this surface to volume ratio is decreasing. So that means the heat emission dissipation is less. So the next option is the resistance to current flow decreases since the conductivity increases. The resistance to current flow decreases. That is true. Since the conductivity increases, that is also true because we are having increase in radius, so increase in conductivity, electrical conductivity, hence decrease in resistance. This is inverse. So this option is correct. The arc uh, the arc bulges out and the resistance to current flow decreases. No, the arc will be cylindrical. This is wrong. Only till now, only second option is correct. We can we can eliminate B. So now see, and first options are wrong. So we can eliminate this out as well. Let us see third option. Third option is also wrong. So we have to go for other option. The arc bulges out and the resistance to current flow increases. No, arc will not bulges out. Will not bulge. So option D is wrong. So the correct option is C. Let us see the option as well. The arc displays less heat since the radius increases and the shape remains cylindrical. Yeah, this is the correct statement as I discussed here. Okay. If you want more clarification, so below 50 amps, what happens is, so the shape of the arc is cylindrical. Okay, and it will increase. This and this radius is going to increase. So the radius is increasing. That means the surface to volume ratio is decreasing. That means heat dissipation is decreasing. Then, since the radius is increasing, the resistance decreasing. That means conductivity increasing. That means voltage is decreasing. Okay, this is what happens below 50 amps. Okay, but above what happens? This radius will increase and it will bulges out. So once it bulges out, all the characteristics is going to change. Okay, that is all about this current characteristics of arc. If you have any doubt, just remember the graph. Yeah, this graph. So for a given electrometal, the voltage reduces with increase in current, and then it will increase. So the deciding our saddle point is 50 amps. So until 50 amps, the shape of the arc is almost cylindrical. The surface volume to ratio decreases with increasing radius. So it is a chain reaction happening. So shape remains cylindrical, that dissipate less heat, conductivity increases, resistance decreases, and voltage decreases. But what about 50 amps? The arc bulges out. The current path becomes more than the arc gap. Resistive current flow increases and the voltage increases above 50 amps. Okay. So that is all about this arc characteristics. So let us see the next questions as well. So these are the last two questions. Spend some time and I'll explain later. Okay, good. So let us see about ninth question. During solidification of weld pool, an increase in strength occurs due to. Okay. So slow killing of the mortal element in the pool? No, it is always very fast. Okay, it's not slow. Rapid heat transfer to the cold parent metal? Yeah, this is true because it is faster. And then actually quenching effect of the molten metal, that is true. I think in the previous section I have explained this. So we'll come across very often like so so finer grains are produced in casting because of the um, if the mold are made of metals. Okay, that is like quenching effect that is going to happen. So two and three are correct. One is wrong. One is wrong. We do this. Two and three correct. Then let us see the other options. Generation of final gains. Yeah, this is also true. The final gains are generated. Okay. Then normalization effect in the open air. No, it's not going to happen. Normalization is not happening. Okay. So only option three and four are correct. No, generation of final caps is also wrong. Only this is the after effect, but the main reasons for the strength is these two. Only option B is the correct answer. So rapid heat transfer to the cold parent matter and the quenching effect that is going to happen. Okay, finer grains are happening, but it's not the case. The reasons is the above are the reasons 2 and 3. Can delete this as well. So option B is the correct answer in for question number 9. Okay, then let us see next question. Question number 10. Building defects such as porosity can be prevented by. If you remember, this was the latest discussion that we have given. So porosity mainly occur if the gases are absorbed into the melt pool, and if the gating design is not good, then it's going to happen. So not getting the weld selection is if the electrode or filler is not selected properly. Okay, then so let us read the options. Preheating of the build area. Yeah, this will clean the surfaces and then remove these porosities and defects. Provide adequate shielding gases. No, this shielding gases okay, but it's not accurate. Proper selection of electrode and pillar yeah, this is the true one. Proper cleaning and preventing of contaminants from the entering the build zone. So this is also true. Provide adequate shielding gases. Here, shielding gases do prevent, but the gases are being absorbed into the whirlpool. That is not going to be, prevented by using these shielding gases. So you have to use some flux to oxidize these metals and remove. Okay, only option one is correct, so you can remove this. Then option three is also correct. Option two is wrong. So option D is the correct statement. So for the question number 10, we can go with option D. Which welding defects such as porosity can be prevented by preheating the weld, proper selection of electrode and filler materials, proper cleaning and preventing contaminants from the entering the weld zone. So this is a defect that we discussed. Proper selection, preheating of the weld, proper cleaning and preventing the contaminants. So we don't have to think in generalized fashion. So whatever is provided to our slides, we can limit our thing capability it. So these are the some basic topics that are being covered on this casting and joining process, and there are several other topics that has to be covered. If you're interested, you can go through the textbooks. So this ends this 4-week course on joining and casting and joining process. So all the best for your the exam, the register show. If possible, if there is any session, we'll intimate you if any final session needed. And thanks for joining. If you have any doubts, we can discuss. Otherwise, you can continue with your work. Thank you. Yeah, thank you. So these notes and lectures are available if you go to the NPTEL website, and if you see the problem solving section on the left side corner, left side bottom, you see problem solving, in which you'll be directed to a spreadsheet, and in that spreadsheet you'll have this Google Drive links for these slides as well as recordings. So if you have any doubts, you can refer to them. Thanks. Okay, thank you. So I'm ending the session.